Think, Build, Scale, a podcast that disrupts conventional consulting businesses. Because in this podcast, you get a lot more than your typical consultant, and all of that for free. All you need is to provide some time and attention, which of course is the most valuable asset of an entrepreneur. Hence, if you are new to this podcast, I want to explain the flow of the episodes. Each month, a new topic will be discussed. This month, it is hydrogen automotives. Each topic will contain 3 episodes. This is the 3rd episode for hydrogen automotives. Before I go ahead, I want to bring to your attention that no company secrets or confidentiality agreements have been or will be violated consciously while recording the episodes of this podcast. Everything presented here is an amalgamation of knowledge and experiences from various industries and trainings that I've had so far. The information presented here, to the best of my knowledge, does not overlap with any confidential information that would fall within the trade secrets of any of the companies that I have had non-disclosure agreements with within the last 2 decades. All right. 3rd episode. It's all about overcoming the operational challenges of a business centered around hydrogen automotives. Look at this. Look at this slide. What does it say? Hydrogen refueling infrastructure and compatibility, a critical challenge for FCEVs. Fuel cell electric vehicles are relying on hydrogen as their primary energy source, but one of the most significant barriers to their widespread adoption is the lack of a fully developed, standardized, and cost-effective refueling infrastructure. In other words, there are no hydrogen refueling gas stations. There are no charging stations. As simple as that. Even if you have a car, it's expensive. What are you going to do? Anyway, unlike battery electric vehicles, which benefit from widely accepted charging standards such as CCS and CHAdeMO and Tesla superchargers, hydrogen refueling remains highly fragmented and technologically complex. For hydrogen refueling stations to be effective, safe, and scalable, extensive research and development investment is required in several key areas. Number 1 is the fast refueling compatibility. So, hydrogen dispensers and vehicle fuel tanks must support high flow refueling to match the speed of gasoline or diesel refueling. And the target is actually under 5 minutes. At this stage, it's not the case. Compatibility issues differ between different station providers and vehicle manufacturers. There is a need for real-time pressure and temperature adjustments to prevent fuel system malfunctions. We need to have the R&D focus that should go for this challenge is on the development of high throughput refueling systems with dynamic flow rate adjustments, standardization of fueling connectors, hoses, and nozzles across manufacturers, enhanced sensor-driven safety mechanisms to prevent overpressurization and temperature instability. The second challenge is hydrogen pressure and temperature control during refueling. What does it mean? So hydrogen refueling involves compressing hydrogen gas up to 700 bar, that is 10,000 psi, and cooling it to minus 40 degrees centigrade to ensure fast and efficient tank filling. Maintaining the correct pressure and temperature balance is essential for safety, fuel quality, and vehicle compatibility. Challenges are that hydrogen compression and cooling require significant energy, making it extremely expensive. Temperature spikes during refueling and can lead to incomplete fills or safety risks. Station-to-vehicle communication must ensure the FCEV tank can handle the given pressure. Required R&D focus in this area is to have smart pressure-regulated systems to adapt to vehicle specifications in real time, advanced hydrogen pre-cooling technologies to prevent overheating and underfilling, integration of AI-based safety monitoring to detect anomalies in pressure and temperature. Automated hydrogen dispensing systems, there's also a challenge there because unlike gasoline or EV charging, hydrogen refueling requires precise automated and high-pressure dispensing systems to ensure safety and efficiency. Current hydrogen dispensers require manual operation, but fully automated refueling systems would enhance convenience and reduce risks. What are the challenges? Complexity of automated nozzle attachment and sealing at 700 bar. I mean, that's not a joke. The pressure at which the hydrogen is stored, it's not a joke. So, ensuring leak proof connections to prevent hydrogen loss or safety hazards. And then you have machine learning, fuel flow optimization to minimize waste and optimize fill speed. What's the required R&D focus here? For safer and faster fueling, robotic or semi-automated hydrogen dispensing systems should be developed. Smart hydrogen nozzles that adjust the pressure dynamically based on vehicle input. And then your wireless communication between stations and FCEVs to optimize fill patterns. Because every brand will be different because of manufacturing differences. Even within the brands, every vehicle would be at least a slight bit different. But yes, that's why we need wireless communication between the vehicle itself and the charging stations to really optimize and figure out the flow and the amount of, the flow of filling, but also the time that is required to fill it up. Why are these kind of investments needed? I talked about investments in fast refueling compatibility. I talked about hydrogen pressure and temperature control during refueling, and I talked about automated hydrogen dispensing systems. Why are these even needed? Because hydrogen refueling faces major standardization hurdles today. Unlike EVs, which have universal connectors and charging protocols, hydrogen refueling is still evolving with no globally accepted standard for fuel nozzles, pressure regulation, or dispensing technology. Each automaker and refueling station provider must develop proprietary solutions, increasing cost and complexity. Hydrogen storage and dispensing requires advanced engineering. Storing hydrogen at high pressure, up to 700 bar, requires specialized tanks, advanced insulation, and ultra high strength materials. Improper handling can lead to hydrogen leaks, inefficiencies, or even explosions, necessitating state of the art safety measures and automated controls. Developing a scalable hydrogen economy requires massive amount of investment, and no company, I repeat, no company should be doing it alone. Government should be helping them. Continents should come together to work on a scalable hydrogen economy. Unlike the EV market, which benefits from expanding grid-based charging network, hydrogen refueling stations require standalone high-pressure storage, cryogenic cooling, and energy-intensive compression systems. Reducing infrastructure costs through better R&D will make your FCEVs more commercially viable. There are some key investment areas for hydrogen refueling infrastructure. Number one is the high flow hydrogen dispenser. Two is the cryogenic hydrogen storage and compression. And then the third is the fast refueling algorithms and communication systems. I will talk about that later, but I want to discuss a little bit about your leading developers and innovators who are actually working in these areas. Air Liquide. Air Liquide is a global leader in industrial gases, developing high pressure hydrogen storage and dispensing solutions for refueling stations worldwide. They have partnered with major automotive companies to deploy hydrogen corridors in Europe and North America. Linde. Linde is pioneering in cryogenic hydrogen storage and compression technologies for refueling stations. They're focused on scaling up hydrogen infrastructure to make it commercially viable for FCEVs and heavy transport. Toyota, a key player in FCEV development, Toyota Mirai, and hydrogen refueling standardization. They're investing in high pressure automated refueling technologies to expand global infrastructure. Plug Power focuses on hydrogen fueling solutions for commercial and industrial applications, developing modular hydrogen refueling stations to support FCEVs and hydrogen-powered forklifts. Conclusion of the future of hydrogen refueling is that while hydrogen fuel cell technology offers immense potential for zero emission, transportation refueling infrastructure remains. While hydrogen fuel cell technology offers immense potential for zero emission transportation, refueling infrastructure remains a major bottleneck. Unlike BEV charging, which benefits from existing electrical grids, hydrogen refueling requires entirely new infrastructure, including high pressure storage, automated dispensing, and temperature controlled fueling systems. To make FCEVs commercially competitive, massive R&D investment is needed in standardizing hydrogen refueling protocols, in the storage systems of hydrogen, and in, of course, the real-time pressure and temperature control of the refueling systems. One of the biggest hurdles in hydrogen economy is building a hydrogen refueling station. The hydrogen fuel cell electric vehicles, or FCEVs, have the potential to revolutionize transportation. But for that to happen, we need a solid refueling infrastructure. Unlike EVs, charging stations, which can be installed just about anywhere with access to electricity, a hydrogen refueling station requires a dedicated supply chain, specialized storage, and advanced safety systems. Hydrogen production and delivery. Hydrogen can be produced in multiple ways: electrolysis, natural gas reforming, or biomass conversion. But transporting and storing it, that's the logistical challenge. Do we produce hydrogen on site, or do we truck it from large scale production facilities? That is an important question. Storage. Hydrogen has to be stored either as a compressed gas at 700 bar or in liquid form at cryogenic temperatures at minus 253 degrees centigrade. Each method has its pros and cons, but they both require specialized tanks and safety measures. Land and zoning regulations. Building a hydrogen station requires approvals from local governments, fire marshals, and environmental agencies. Not every location is suited for high pressure gas storage. How to overcome this? Modular hydrogen stations. Companies like Air Liquide and Linde are developing compact modular hydrogen stations that can be deployed faster. Co-locating with existing fuel stations. Many hydrogen refueling stations are now being integrated into existing gas stations to reduce land acquisition challenges. On-site hydrogen production. Instead of transporting hydrogen, some stations are opting for on-site electrolysis, reducing logistic costs and increasing efficiency. Refueling technology and safety challenges. We have to really talk about this. Hydrogen refueling is much more complex than plugging in an electric car. Hydrogen dispenser must manage pressure, temperature, and fuel flow rate while ensuring the vehicle's tank does not exceed safety limits. The pressure control. Hydrogen is stored at 700 bar, and refueling must be carefully managed to avoid overheating. Cryogenic handling. Liquid hydrogen must be handled at near absolute zero, reaching advanced insulation and special transfer technology. Smart nozzles and communication systems. Unlike gas pumps, hydrogen refueling systems need digital vehicle communication to adjust flow rates and pressure dynamically. Safety and leak prevention. Hydrogen is highly flammable, meaning stations require advanced leak detection, emergency shutdown systems, and explosion-proof components. How to overcome this? Advanced dispenser technology, refueling technology, and safety challenges. Hydrogen refueling is much more complex than plugging in an electric car. A hydrogen dispenser must manage pressure, temperature, and fuel flow rate while ensuring the vehicle's tank does not exceed safety limits. Pressure control. Hydrogen is stored at up to 700 bar, and refueling must carefully be managed to avoid overheating. Cryogenic handling must be handled at near absolute zero, requiring advanced insulation. Smart nozzles, unlike gas pumps, hydrogen refueling systems need digital vehicle communication. Safety and leak prevention. Hydrogen is highly flammable. We talked about this earlier in the previous episode, meaning stations require advanced leak detection, emergency shutdown systems, and explosion-proof components. We also talked about it that these things are also needed for the vehicle itself. How to overcome this? Companies are developing smart nozzles with automated locking mechanisms and real-time pressure monitoring. So that's a good thing to look out for. All right, cost and economic viability challenges. Hydrogen stations are expensive. Each one can cost between 1.5 to 3 million to build, only to build. And then forget about the raw materials, forget about like the equipment cost, etc. Just to build, you need 1.5 to 3 million. Why is it so expensive? Because you use high-tech equipment. Hydrogen storage tanks, compressors, and dispensers are far more expensive than conventional fuel pumps. You have low utilization rates. Unlike gas stations, hydrogen refueling systems serve a small customer base, making it difficult to turn into a profit. That's why you need government incentives so that the government can provide subsidies for customers to bring it to a mass deployment stage. How to overcome this? Public and private partnerships, hydrogen hubs where you have clustered multiple stations in key urban areas, and you have heavy duty vehicle integration. You should focus on fleets such as buses and trucks. They ensure steady demand, and they make use of stations, and that makes the overall hydrogen economy more financially viable. Public awareness and adoption challenges. Like finally, there's the human factor. Many people don't understand hydrogen technology, and automakers have been slow to roll out FCEVs due to concerns about refueling availability. Hydrogen is often perceived as dangerous because of its high flammability. Only a handful of manufacturers like Toyota, Hyundai, and Honda currently offer FC. Infrastructure catch-22 is that automakers won't produce more FCEVs unless stations exist, but companies won't build stations without more vehicles on the road. How do you overcome this? Well, how do you overcome this? Industry leaders need to educate people on hydrogen safety and benefits. Policies from the government that encourage FCEV production and hydrogen station expansion can break the cycle of slow adoption. Hydrogen adoption is more likely to grow through fleet applications before reaching mass market consumers. Here are some fuel cell electric vehicles currently available in the market. You have Toyota Mirai that has started between 2023 to 25. The range is around 400 to 450 miles at this stage. And then you have hydrogen consumption of 5.6 kilos per 100 miles. And you have advanced features like digital cockpit and autonomous driving support. You have Hyundai Nexo that has distance per 1 kilo would be 15.87 miles. Distance per 1 kilo of hydrogen. And then you have your Hyundai CRV hydrogen, Honda CRV hydrogen. The distance per 1 kilo would be 14.71. Hyundai Exient fuel cell truck will go 5 miles per 1 kilo of hydrogen. Toyota Kenworth is going to go 4.55 per 1 kilo of hydrogen. Nikola Tre FCEV will go 5.56. Mercedes-Benz and Van Hool Exquisity buses are at quite low. I'm sure these are hybrid solutions. But in general, Toyota Mirai provides advanced features in digital cockpit. Your Hyundai Nexo offers level 2 ADAS and large touchscreen infotainment. Honda CRV combines battery, electric, and hydrogen fuel cell technology, as I would expect. And of course, there are several other EVs out there, but yeah, the situation at this stage is not very profitable for the average consumer. If you look at hydrogen cost and distance per USD, so in North America, this is one of my favorite research tables that I have made during my research. So one of the biggest reasons is just cost. Like that's the reason why you don't see hydrogen automotives taking up so easily. So the distance per USD that you can go in North America in kilometers is 1.79, in miles is 1.11. So that's per 1 USD. I mean, you have to like think about this. For each dollar in North America, you can go 1.11 mile. And right now, Asia, China is actually leading in the cost run. Sorry, actually, South America and Africa are leading in the cost because I think lower infrastructure and OPEX costs. But in general, if you look at Europe, it's 1.7 kilometers per USD. In Asia, you can travel 2.24 kilometer per $1. Australia, you can go 1.93 kilometers per $1. South America, 2.49, and Africa, 2.84. So yes, we need a significant amount of R&D investment here on figuring out how to effectively improve. And in my previous episode, I have mentioned several different components that you can look at and where to concentrate if you want to bring the cost of your hydrogen automotive down. But it's not always about the cost of the hydrogen automotive. It's really about the refuelings, because here we are talking about the refueling infrastructure of the hydrogen. So yeah, it requires a good amount of thought and strategy from the government itself. All right. Reducing the cost of hydrogen production is critical to making FCEVs and hydrogen infrastructure economically viable. Here are the key strategies. We need to scale up green hydrogen production. Current challenge is that green hydrogen comes from electrolysis and is expensive due to high electricity costs and low electrolyzer efficiency. So we need to have mass production of electrolyzers so that the production price per unit decreases of these electrolyzers. Then you need larger electrolysis plants. We need to deploy gigawatt scale hydrogen production, and this will lower operational costs. Then we need renewable energy integration as well. So using excess solar and wind energy for hydrogen production, this will lower electricity expenses significantly. Improving electrolysis efficiency. The current challenge is that the electrolyzers require a lot of energy and have inefficiencies in conversion. So solid state electrolysis uses waste heat to improve efficiency. Advanced catalysts, they replace platinum and iridium with cheaper alternatives. With AI and automation, we can optimize electricity use during hydrogen production. Now, lowering the cost in blue hydrogen, which is fossil fuel based hydrogen. How do you do that? Blue hydrogen, which is from natural gas, still produces carbon dioxide, and it requires expensive carbon capture and storage. So more efficient carbon capture and storage technology would need to be discussed and invested upon. And this would be a next generation capture tech. You have methane pyrolysis. This produces solid carbon instead of carbon dioxide, making carbon handling easier. And you have waste to hydrogen that converts biomass and plastic waste into hydrogen. Reducing hydrogen transport and storage costs. Current challenge is that hydrogen is light and volatile, making storage and transport expensive. Liquid hydrogen carriers, which is ammonia and liquid organic hydrogen carriers for easier transport. Pipelines instead of trucks. Expanding hydrogen pipelines lowers transportation costs. And then, so I'm suggesting more like your fiber optic pipes that you're being used to actually transport your data. So we need pipelines like that for hydrogen transport and storage. It's very difficult and it's a very massive task. Your local on-site hydrogen production, electrolysis at refueling stations remove the need for transport. All right. Government policies and incentives. Well, you need subsidies. You need carbon tax on fossil fuels, and you need hydrogen trading markets. As simple as that. Industrial and commercial demand growth. Well, low hydrogen demand keeps prices high, and you need heavy industry adoption where steel, cement, and chemical industries use hydrogen at scale. And then you have hydrogen powered fleets. Expanding FCE trucks, buses, and ships increase volume and will eventually reduce the cost of components, refueling into infrastructure, etc. It's converting hydrogen into e-fuels for aviation and shipping. That would help a lot in reducing the cost. Conclusion: bringing hydrogen below $2 per kilo. By combining scaling, efficiency, and infrastructure improvement and policy support, the hydrogen industry can drive cost below $2 per kilo, making FCEVs and hydrogen based industries competitive worldwide. But it's still not enough to replace electric vehicles. That's the thing. In order to have a cleaner earth and a cleaner environment, we need time as human race, and we need a lot of investment and a lot of strategy. But most importantly, time, time, and time. That's the trick. That's the real trick. All right. I want to talk about what different countries and continents are actually working on. So in Saudi Arabia, you have something called NEOM Green Hydrogen Project. Their goal is to have produce green hydrogen, 4 gigawatts of green hydrogen at a cost below $1.5 per kilo. How do you do that? Mass scaling electrolysis powered by 100% solar and wind energy, advanced water electrolysis with AI-driven efficiency optimization, and then hydrogen to ammonia conversion for cost-effective transport. The impact is that it's expected to export 650 tons of hydrogen per day and first commercial scale hydrogen hub globally, and to establish the first commercial scale green hydrogen hub globally. US Hydrogen Hubs program. Well, the goal is to develop multiple regional hydrogen hubs to lower production and customer and transport costs. How? Public-private partnerships between US government and companies like Air Liquide, Plug Power. Infrastructure first approach, build pipelines and storage to scale up production. Tax credits under the Inflation Reduction Act to incentivize production. Impact. This program is expected to reduce green hydrogen cost below $2 per kilo by 2030. So increased private sector investment in large-scale electrolysis. China's national hydrogen strategy. So China is scaling hydrogen adoption across transport, industry, and power sectors. Hydrogen-powered steel plants reduce carbon emission. Largest fleet of hydrogen buses and trucks globally are found in China, actually. Hydrogen refueling corridors connecting major cities are available in China. Production cost is reduced to around they currently have reduced to around $2.50 per kilo in many regions in China. And the government is targeting less than $2 per kilo by 2030 with industrial scale adoption. Australia's green hydrogen export plans is to become a leading hydrogen exporter to Japan and South Korea. They want to have massive solar to hydrogen projects, and then they are investing more than $2 billion in electrolyzer scaling and storage, hydrogen liquefaction, and ammonia conversion for efficient shipping. The impact is that this program is expected to export hydrogen at less than $2 per kilo by 2028. But be mindful that the logistics cost will eventually make it less competitive with your EV and other hydrogen automotives. Partnerships with Japan and Germany are going on from Australia's side. Yeah, the European hydrogen backbone. Well, the goal for Europe is to build a transcontinental hydrogen pipeline network to cut transport costs. How? They're going to convert existing gas pipelines to carry hydrogen, reducing dependency on trucking and liquefaction, which is very expensive. EU Green Deal incentives support large scale adoption impact, projected to reduce transport costs by 80%. Expected hydrogen cost in Europe to reach $2 per kilo by 2030. As you see, Europe is a little bit behind in its roadmap than many other places across the world. The National Green Hydrogen Mission, the investment there is around 2.3 billion from the government of India. Goal is to have 5 million metric tons of green hydrogen annually by 2030. The strategy is to scale electrolyzer production, integrate renewables, expand refueling infrastructure. The goal is absolutely to have hydrogen below $2 per kilo. Indian automakers advancing hydrogen vehicles, Tata Motors, Ashok Leyland, and Toyota Kirloskar. So Tata has already developed hydrogen buses and heavy duty trucks. They're having pilot run soon. And then you have the hydrogen trucks and hydrogen ICE engines from Ashok Leyland. This is a fleet logistics company. All right. The government policies and incentives, electrolyzer subsidies and tax benefits for hydrogen fuel cells, and fleet trials and infrastructure funding is going on. And the projected cost reduction from $7 per kilo at this stage to less than $2 per kilo by 2030. That is India's goal. Roadmap to hydrogen below $2 per kilo. Well, to bring hydrogen below $2 per kilo, you need a multifaceted approach. 2025 to 30, the government should focus on mass scale electrolyzers and hydrogen hubs to bring green hydrogen to $2.5 per kilo. Hydrogen pipelines, LOHS, liquid organic hydrogen compressed. 2025 to 2030 marks 2025 to 30. Mass scale electrolyzers and hydrogen hubs bring green hydrogen to around $2.50 per kilo. Hydrogen pipelines and liquid organic hydrogen cooling and AI optimization cut costs by around 30%. 2030 to 40, we can expect breakthroughs in electrolysis. Your AI-driven efficiency and nuclear biohydrogen reduces prices up to $1.50 per kilo. Global adoption in industry, transport, and energy storage ensures sustained cost reduction. So yes, it's not a matter of, it's definitely going to take more than a decade to really see that hydrogen automotives are becoming norm, and it will take around 20 more years to see that it's becoming a household name. So yeah, the road is quite strenuous, I would say. Key technologies driving hydrogen costs below $2 per kilo. So you need high efficiency electrolysis technologies. Here you have your solid oxide electrolysis cells. Need electrolysis converts water into hydrogen, as we all know, and it increases efficiency and reduces energy losses and lowers cost. If you have waste heat from industries, SOECs can utilize the waste heat and can reduce energy consumption. Developed by Bloom Energy, Sunfire, and Haldor Topsoe, being integrated into, we start again. Okay. Key technologies that will drive hydrogen costs below $2 per kilo. Number one is to use high efficiency electrolysis technology. Electrolysis converts water into hydrogen using electricity. Increasing efficiency reduces energy losses and lowers costs. So your solid oxide electrolysis cells, they have a good efficiency of 80 to 90%. It is also a bit cheaper because it uses waste heat from industries and it reduces electricity consumption. It's actually developed by Bloom Energy Sunfire and Haldor Topsoe. This is actually a real world case. So being integrated into steel production for ArcelorMittal to cut emissions and lower hydrogen costs. So protein exchange membrane electrolyzers, the efficiency is around 75 to 85% and is cheaper because it's more compact and modular than traditional alkaline electrolysis. It requires less water and operates at lower temperature. Real world use case used by ITM Power, Nel Hydrogen, and Plug Power for green hydrogen hubs. Alkaline electrolyzers, their efficiency is around 65 to 75%, and they are cheaper because they have lower capital expenditure, or the initial investments is a bit lower than your PEM and your SOEC systems. PEM is your proton exchange membrane system, and SOEC is solid oxide electrolysis cells. All right. And the good thing about alkaline electrolyzers is that it has abundant nickel. It uses abundant nickel catalysts instead of expensive platinum or iridium. And real world application for this is that in China is quite common that in hydrogen power plants, alkaline electrolyzers are used. So cost reduction potential would be that mass producing electrolyzers can cut costs by 50% by 2030. Gigafactories like Siemens and ITM power plants, they actually aim to reduce capex, your capital expenditure, by 70% just by looking at high efficiency electrolysis techniques. All right, the low cost hydrogen transport and storage. Why does it matter? Transport and storage accounts for 30 to 40% of hydrogen costs. Hydrogen pipeline, that is a very essential project. The hydrogen backbone project is a very important thing that, just like our fiber optics and internet cables, it's all over the world and is working with a network. We need to create such pipelines for hydrogen, such literal pipelines that would go underneath the surface of Earth and transport hydrogen from one place to another. That's the only way we can make it cheaper. Why is it actually cheaper? It's 10 times cheaper than trucking hydrogen over long distances. Remember that. And you're actually using fuel sources or electricity if you're actually using trucks. Real world use cases. The European Hydrogen Backbone Project will connect 21 EU countries with 40,000 plus kilometers of hydrogen pipelines by 2040. Liquid organic hydrogen carriers. Why is it cheaper? It stores hydrogen at ambient temperature and pressure, eliminating cryogenic storage costs, and it can be transported using existing fuel infrastructure. Hydrogenous LOHC technologies and Chiyoda corporations are commercializing LOHC for large scale transport. Ammonia as a hydrogen carrier. Ammonia stores hydrogen effectively, efficiently, and is easier to transport. It can be directly used in fuel cells or cracked back into hydrogen. A real world application would be Japan and Australia's hydrogen export projects. They're using ammonia based transport. Saudi Arabia's NEOM hydrogen project will export ammonia based hydrogen globally. Cost reduction potential for this is that for pipelines and LOHCs, it can cut transport cost by up to 80%. And ammonia-based hydrogen can reduce shipping costs by 50%. AI and automation for cost optimization. AI can predict demand, optimize energy use, and prevent inefficiencies. AI can adjust hydrogen production based on electricity prices and use power when it is cheaper. It is the cheapest. A real world use case is the H2 Pro and Sunfire. They are integrating AI based optimization into hydrogen production. In fact, many solar power companies are now starting this system where, based on AI algorithms, depending on the time of the day, whenever it's sunniest or it's cheapest, you can utilize more energy. And when it is not so cost efficient, you are using energy from a stored battery in your house. And that's already happening. So it's the same model for AI optimized electrolyzers as well. Many people also talk about digital twins for hydrogen infrastructure. Why is it cheaper? It's because it simulates hydrogen production and transport in real time, allowing automated adjustments to cut waste. This is more of a managerial tool, to be honest. Siemens and ABB are deploying digital twin models in hydrogen hubs. Digital twins should always be taken with a grain of salt because physical world is entirely different and turbulent, more turbulent than your digital twin world. Okay. AI-driven optimization can cut hydrogen production costs by 20%. Digital twins can improve infrastructure efficiency by 30%. Carbon-free hydrogen form nuclear and biomass. Why does it matter? Beyond electrolysis, new low-carbon hydrogen sourcing are emerging. High temperature nuclear hydrogen, which is HDR and SMR, they're actually a bit cheaper. Nuclear reactors can provide heat for hydrogen production, reducing energy costs. Real-world use case for this would be Japan's HTTR project and US's DOE SMR-based hydrogen project that are piloting nuclear-driven hydrogen. Now, biomass to hydrogen. Why is it cheaper? Because it uses agricultural and industrial waste to generate hydrogen. Real world use case would be your Hazer Group and SGH2 Energy. They are scaling waste to hydrogen plants. Cost reduction potential is that nuclear hydrogen could reach 1.5 per kilo with reactor advancements, and biohydrogen could bring down the cost up to $1.2 per kilo in waste-rich regions. All right. We have talked so much about the infrastructure. Why that? It's because whether you're an established organization or a startup, a scale-up, an SME, doesn't matter. The infrastructure has to be there for your product, your automotive, to fly. So let's assume that a business is able to achieve hydrogen fueled cars and is in a time and place where hydrogen cost is less than $2 per kilo. Remember, what I'm saying is, let's assume that a business is able to achieve hydrogen fueled cars. So you are able to manufacture and develop hydrogen fueled cars. And you are also in a time and place when and where the hydrogen cost is less than $2 per kilo. Because if you don't meet these conditions, there is no use producing your car. You need to have the cost of the hydrogen refueling to be less than €2 two USD per kilo. I mean, it's imperative. You cannot have it more expensive than two USD. So let's assume you meet these criteria. How can a business like that scale? 10-year scaling strategy for your business that is in FCEVs. Years 1 to 2, mass production and cost reduction, standardize FCEV supply chains. Year 3 to 4, expand hydrogen refueling networks, on-site production and mobile refueling. Years 5 to 6, fleet adoption strategy, focus on taxis, buses, logistics, and leasing models. Year 7 to 8, heavy duty industrial expansion, hydrogen trains, trucks, and maritimes, and then maritime transport. And year 9 to 10, carbon credit monetization and international expansion. You can go with a global hydrogen adoption at this stage. So this is a 10-year scaling strategy, very, very realistic strategy for your company, whether you are a startup, SME, or an established organization. Let's go a little bit deeper in these phases. The first 2 years will be all about mass production and cost reduction. So the objective is to ensure that the FCEVs are affordable and scalable before large-scale deployment. Key challenges would be your fuel cell vehicles are more expensive than your EVs and your ICE vehicles. You have limited supply chain for fuel cell stacks, your storage tanks, and components. So your strategic action should be a modular fuel cell stack development, local supply chain development, high volume production, and partnering up with OEMs, and of course, exploit government subsidies and tax breaks. Cost of FCEVs, I hope for you, for your organization, if you take good strategies on innovation as well as on your OPEX scale, FCEVs could drop below $35,000. This is quite in par with your today's standard electric vehicles. Supply chain automation optimization requires fuel cell component costs to be cut down by 40%. First fleet orders secured for pilot hydrogen vehicle programs. This should help you significantly for the later stages of reducing costs. All right. Years 3 to 4, hydrogen infrastructure expansion. Well, you have to install electrolyzers at refueling stations to eliminate transportation cost. Deploy tanker trucks for flexible refueling while permanent stations are built. Develop hydrogen refueling stations along major logistics and public transport routes. Public-private partnerships, PPPs, partner up with governments and energy companies to co-develop refueling stations. Set up dedicated refueling depots for taxis, delivery trucks, and municipal buses. This way, you could expect that the cost drops down to 30% due to on-site production. Fleet operators gain confidence in FCEV infrastructure. Therefore, higher adoption takes place. And the first publicly accessible hydrogen stations open up in urban hubs. Phase 5 to 6. The strategy should be that you provide leasing options for hydrogen taxis, similar to EV taxi adoption in China, actually. Deploy fuel cell delivery vans for Amazon, DHL, FedEx, etc. Scale production of city buses for transit agencies in large cities. Reduce upfront costs with subscription-based hydrogen vehicle services, and partner up with auto manufacturers to ensure resale value for FCEVs. So your expected outcome during these years would be that around thousands of hydrogen taxis, delivery trucks, and buses are being adopted in major cities of the world. FCEVs achieve widespread fleet adoption before full consumer rollout. Hydrogen fuel demand increases and supporting stations also expand. Phases 7 to 8 is expansion into heavy duty and industrial transport. So here you need to expand FCEV semi trucks for logistic operations like UPS, Walmart, Maersk. Deploy fuel cell powered freight trains and passenger trains. Introduce hydrogen powered cargo ships and ferries. Develop fuel cell mining trucks, excavators, and port equipment. So, what's the outcome here? The expected outcome would be that you dominate long haul logistics. Heavy duty hydrogen vehicles can become an industry standards, and port and railway networks integrate into hydrogen refueling hubs. Final 9 to 10 years is a global expansion and market leadership for your hydrogen automotive business. Monetize hydrogen investments, expand internationally, secure long-term profitability. And then, of course, leverage carbon credits and government incentives, expand into high hydrogen markets, license hydrogen powertrain technology, scale renewable hydrogen production. Expected outcomes would be that hydrogen powered transport achieves mainstream adoption. FCEVs become cost competitive with EVs and gasoline cars. Business secures global market leadership in hydrogen mobility. There you go. This is a 10-year dummy financial projection for scaling a hydrogen-fueled automotive business, including revenue, CAPEX, OPEX, and net profit trends. So here you go. From year 1 to 10, you first start. I'm gonna have a pointer. Year 1. In year 1, you start with a revenue of 0.2 billion, and your CAPEX is quite high, 2 billion. Your OPEX, your operating expenses would be 0.5, but you actually make no profit. You see, up to around year 6, you are actually making not much profit. From year 7 onwards, you will slowly start making profit and start scaling up. Why is that happening? Because what's happening at year 7? You're expanding into heavy duty and industrial transport. This is where the money lies, and this is where it helps to integrate. It gives confidence to integrate hydrogen refueling hubs all over and making it more mainstream. CAPEX refers to long-term investments made to build and expand the business, and these are one-time costs. OPEX is your operational costs, your employee salaries, hydrogen production costs, your fuel logistics cost, maintenance and repairs, marketing and sales. These are OPEX. For one, I'm hoping for a future where we can see cars all around us use the cleanest and most efficient fuel called hydrogen. I shall now close this topic in this podcast. The next topic would be battery technology, and this topic caters to automotives, aerospace, outer space, commercial electronics, and industrial electronics. Thank you for watching. Have a beautiful rest of the day. I will see you in the next topic. That will be battery technology. Bye-bye.